Okay, cool. I'll kick things off then. So hi everyone. My name is Callum McPherson. I'm from a physics background originally, but I work for Quantinuum in the quantum software team. I work on TKET, and today I'm going to be giving you sort of an intro overview to quantum software in general, and also the TKET project that I work on. So a couple things to mention before I start is that the second section of my talk will be a Jupyter Notebook demo. So hopefully you've all received a link to my GitHub repository here. So you can hopefully follow along with this notebook if you want to. I've also included some purely optional exercises for you to try as well, if you want something to work on after today. Okay, yeah, the second thing is, I don't know about you, but I much prefer giving sort of informal, chatty presentations. So if I'm going too fast or if I'm saying something that doesn't make sense, then please stop me and I will try and explain uh, something more. Okay, let's get started then. Okay, I've already explained who I am. So let's start things off with a bit of motivation. So I assume that some of you have some idea of why we are interested in quantum computing, but just as a recap, the primary reason that we're interested in quantum computing is that for certain specific problems, quantum computers offer computational advantages compared to classical algorithms. So there are some sort of canonical examples of this, like Shor's algorithm is a very famous example. It offers a near exponential speedup for the factoring problem, which has led people to think about how this could be relevant for RSA cryptography. There's also Grover's algorithm, which is an algorithm for unstructured search problems, and many algorithms for quantum chemistry and material science, and some algorithms which fall into the other category of machine learning or optimization and so on. Yeah, so I'm going to talk about primarily some of the challenges of making these algorithms work on real hardware. So you might know that like some of these algorithms, like Shor's algorithm, they require very large circuits because you need to implement these quantum error correction codes, which typically means you have to have many extra qubits to encode the logical state of your algorithm. Okay, so now that I've given you a one-slide overview of quantum algorithms, let's talk a bit about quantum software. So I've made this sort of distinction between what you might call the system software of a quantum computer, the software that's essential to the operation of the device itself. So there's some well-known sort of libraries for working with quantum computing. The example is Qiskit. Yeah, so Qiskit and TKET, which I work on, is all about building and quantum circuits and then compiling them down to a form where they can actually be run on hardware. Additionally, there are some like online platforms for like actually accessing quantum devices. So you may have heard about the platforms that AWS and Azure have for accessing quantum computers via the cloud. So that's another kind of service that's offered. Additionally, there's some software which relates to error correction or error mitigation, and this is to sort of help resolve any errors which might occur over the course of your computation. And then there's specifically just quantum programming languages. So programming languages based around sort of working with quantum information. So there's some examples like Microsoft's Q#, for instance, or Silk. And there's also what you might call application software. So this is software that scientists working with quantum computers might make use of. So if you're a quantum chemist, for instance, you might have a chemistry library to build your quantum algorithms before you submit them to the quantum computer. So an example would be in at Quantinuum, we have a proprietary library called Inquanto, which is a package for doing quantum chemistry, but there are also packages for doing machine learning and all manner of other things with quantum computing. Okay. Let's now say a few things about quantum hardware. So quantum hardware is interesting in that there are many ways to physically realize a quantum computer. So you may have heard of all these different types of architectures that people are working with and trying to come up with a scalable approach to doing quantum computing. So firstly, we have trapped ions. This is what my company actually works on, mostly on the US side. So yeah, trapped ions are a well-established platform, but we also have superconducting devices from IBM and Google and Rigetti and others, as well as photonics and neutral atoms, and yeah, even more exotic things like topological qubits that people have thought about. In a way, I think it's quite good that people are pursuing many different architectures in parallel, because it means you can, if you're not sure how to build a scalable quantum computer, having many parallel approaches is productive, I think. But yeah, so quantum computing comes with some challenges, so many challenges, and I'll discuss some of these challenges now. So firstly, we don't have enough qubits for some of the most exciting applications. So as I mentioned, Shor's algorithm is a very promising algorithm on paper, but you need many, many qubits to actually run Shor's algorithm for a cryptographically interesting problem, for instance, to break RSA. And the qubits we do have are typically subject to complex noise that's difficult to understand. So at the moment, we don't have sort of a scalable approach to doing error correction. So we have to deal with the errors that are inherent in our quantum system due to decoherence and other noise effects. And also another point that's going to be relevant for what I'll say later is that kind of low-level details actually greatly influence how the device performs. So for instance, if you have a very large circuit, with many gates, each of these gates will have some associated error rate. So having large circuits just means that you accumulate more and more error over the course of your computation, and your results get noisy. So actually reducing the number of gates is a good way to increase the fidelity of your quantum algorithm. Yeah, okay. So let's look at a real quantum device that you can run things on. So here I've opened up a view of the IBM Guadalupe device from IBM. This is a superconducting device with 16 qubits. And we can see that the qubits are laid out in this sort of sparse graph structure. So that's just this graph just represents the connectivity of the device. And then we can realize interactions between our qubits by performing gate operations between only neighboring qubits. And we also have some associated error rate with like the 2-qubit gate, for instance. So like I said, every gate in your circuit will contribute more and more noise to the computation. So if you're thinking of compiling a quantum circuit, then this is perhaps a natural metric to try and minimize the number of these 2-qubit gates. So yeah, let's talk a bit about the idea of compiling to a real quantum device. So very roughly speaking, what a compiler does is sort of take a representation of a program that's readable by humans and converts it to something that can actually be run on a device. So people that design quantum algorithms don't typically want to think about low-level details of the device they're targeting. So some compiler will have to solve for the constraints of the real device. So I've included here an example of a circuit that you might want to run. This is a circuit for the quantum Fourier transform. So you can see I have these single qubit gates, and I have also these 2 qubit gates, which are interactions between the qubits. Quantum Fourier transform, if you're not aware, is a well-known like sort of subroutine in quantum algorithms. So for instance, it appears as part of Shor's algorithm and various algorithms for quantum chemistry. So one useful piece of information to know about your algorithm is how the qubits in your algorithm are connected to one another. So notice that I have 2 qubit gates between all possible pairs of qubits going on in this diagram. So every pair of qubits is interacting with one another. So if I wanted to encode this information in a graph, I could say my circuit has this complete connectivity graph where all of my qubits are talking to one another. And say I want to actually run this circuit on a device. Typically, like say I pick the IBM Bell M device, for instance, this 5 qubit device here. By contrast, this device has a much sparser connectivity. So you can only realize 2 qubit gate operations between neighboring qubits here. So I can only make qubit 0 talk to qubit 1, for instance, or 1 talk to 0 and 3 and 2. So this is a constraint that a compiler must solve if we want to actually run our quantum algorithms. We also have like a restricted gate set here. So in addition to having only nearest neighbor, we also have to convert our quantum circuit to have the right instructions in it for our quantum computer to run. Okay. Okay, so yeah, like I said, some compiler will have to solve for the constraints of this device. So once I've compiled my circuit, I end up with a sort of lower level representation of my circuit. So instead of this nice sort of pattern that my circuit is in, it's now in this sort of less readable format, but you can now run it on a device. So our quantum circuit is now in the right set of instructions, and it also has solved the connectivity constraints have been solved. So it now contains only interactions between neighboring nodes in the device. So you can see node 1 is connected. Yeah, so node 0 only. Yeah, so like this diagram here, so unlike my previous diagram, which had interactions between all pairs of qubits, here I only have nearest neighbor interaction. So that constraint has been met. Okay. Are there any questions so far, or should I keep going? Okay, cool. So now that I've given you a bit of background, I'm going to talk about what I actually work on, which is TKET. So TKET is a software library developed by Quantinuum. And first and foremost, TKET is a high-performance compiler for quantum circuits. So giving a high-level representation of your quantum program or your quantum algorithm, TKET can solve for the device constraints of the device that you're targeting. And it can also target many different types of device as well. So if you are running your quantum circuits on superconducting devices and want to try out, if you're working with superconducting devices and want to try out your circuits on ion trap devices, then that's something you can do through TKET's different extension modules, which allow you to target different backends and simulators interchangeably. TKET's also fully open source. All of our source code is on GitHub. So yeah, feel free to, if you're using TKET, feel free to raise issues or make contributions. Those are all welcome. Oops. So yeah, like I said, TKET is hardware agnostic by design, which means that it's designed to be easy to target, swap out different devices, so you don't have to rewrite your program every time you want to work with a new device. It's also compatible with a lot of other widely used software libraries. So you might have heard of Qiskit from IBM, or Circ from Google, or AWS Bracket. So TKET can work with those libraries as well. So if you write your circuits in Qiskit, you can convert to TKET easily and then compile your circuit and then target whatever device or simulator you want. So TKET is, underneath TKET is a high performance sort of C++ library, but you can access TKET through its Python wrapper. So we call this PyTKET, so sort of Python wrapper around the C++ core. You can install that with just the pip package manager. So pip install PyTKET, and then you can build your circuits and compile them and just use TKET in Python, which is more, I guess, has a simpler interface than working with C++ directly. Yeah, so just as a diagram here, here's a sort of architecture layout, I guess. So like I said, at its core, TKET is a high performance C++ library. So this allows sort of all of the computationally intensive compiler optimizations to run efficiently. So that this is for rewriting circuits. You access TKET through PyTKET, its Python module, and on you have like different front ends for that TKET can work with. So like I said, you can build your circuits in Qiskit and then or Circ or Penny or whatever you like. Then you can translate them to TKET and then compile them. And on the back end, you have different backend, so you can target ion trap devices from Quantinuum, or you can target IBM Q, or a number of other providers, really, through our different extension modules. So we have separate Python packages for interfacing with backends from different providers. And we also can access devices through the cloud as well, through Bracket and Azure. Okay. So that concludes my short slideshow. Now I'm going to actually show you a demo of using TKET itself. Bear with me 1 second. Are there any questions about anything I've covered so far?
I have a quick question.
Yeah, sure.
So like based on this diagram here, you code your quantum circuit with, Qiskit or, whatever you want, and then you sort of send it to TKET, which is a C++ library that's wrapped in Python. But what if I wanted to add something to the right of that? Like I'm doing randomized benchmarking, or I want to add like gate twirling, or some sort of error mitigation that lies in, like, if for that, usually you have to optimize the circuit first and then add in the gates that you want. Is there a way to sort of intercept the gates that TKET generates in Python and then modify, or sorry, the circuits that TKET generates in Python and then modify them?
Yeah, so like maybe this was slightly misleading. So you can actually just you can interface with these different libraries, but you can also just do everything in PyTKET itself. We have an interface for building and representing circuits in there, and we also have a separate error mitigation. We have some error mitigation features which are supported directly within TKET itself, but we also have a bespoke, like a standalone error mitigation package as well. It's called Kermit. It's a bit of a pun with the pun with the name. Quantum error mitigation. It's yeah, a separate library that uses TKET to do error mitigation protocols. So you yeah, you can do things like error mitigation with TKET. People do that. Does that answer your question?
Yeah, definitely. I guess it's just sort of about like, whenever you convert circuits to a different format, if you want to do anything like I guess so for error mitigation, like you could do unitary folding when sometimes to do that in Qiskit, you have to like read the instructions and then like insert gates physically into the circuit. So
Right, yeah.
yeah, so you're saying that like when this ticket library, it doesn't call out directly to the back end, it creates a Python object. And then
Yeah,
you pass
so
that to the back end?
so yeah, the C++ library is just for the high performance sort of rewriting of the circuits. So the extensions that call out to the actual provider are separate sort of Python modules, which interface with the API for whatever provider there is. So yeah, you can do error mitigation protocols. We have some protocols for like doing noise tailoring and things in TKET itself, but like I said, we have a separate library with protocols like implemented for you to experiment with yourself.
Oh, that's fantastic. Thanks.
Cool. Now I'll move to the notebook, actually. 1 second. Did everyone still see my screen okay?
Yep.
Okay, cool. I'm just going to go through sort of a bunch of our different features now and show you how to actually code stuff with TKET. So I'm going to assume some basic familiarity with quantum circuits and a bit Python as well. I hope that's okay. If there's any questions, then just please let me know. So first of all, how do we build circuits? How do we build the most sort of basic circuit we can think of, namely the Bell circuit? So we actually have like a similar interface to other tools like Qiskit for doing this. We have like a circuit class which we can import, and then we can create instance of our circuit class with 2 qubits, and then we can just append gates onto this. So we can apply a Hadamard gate and a controlled NOT between the 0th and 1st qubit. Then we have this like interactive circuit renderer as well. So there are options for like changing the visualization settings of this, which you can play around with. So yeah, one thing we have is like the ZX representation, which is an alternative to the traditional gate-based model. So that's something you can play around with if you like. Yeah. So now that we've built our very basic circuit, how do we, say, run this circuit on like a simulator of some kind? So yeah, here I'm just going to do a basic state vector simulation. I've installed PyTicket, but now I import this backend simulator from the Qiskit extension. This is just the Air state vector simulator. And then I can just initialize my simulator and run my circuit and then extract the state vector at the end. So I end up with this vector here. And if you stare at this for a sec, you'll realize that it's the expected Bell state that we've prepared using the Hadamard and the CX. So this is state vector simulation. What about shots-based simulation? So for this, I can just use the Air backend. I can then append some measurements onto my circuit, which sort of sample from the state vector probabilistically, and I can generate some probability distribution of the different measurement outcomes. So I can create initialize my backend again, and then run my Bell circuit 1,000 times. So I'm just repeating this Bell circuit 1,000 times, and I'm gathering sort of statistics about the different outcomes. So here you run the circuit for 1,000 shots, and you get back this sort of counter object, which is a dictionary where the keys are the different sort of basis states or bit strings, and the values are the number of counts in there. So we have 1,000 we have 1,000 shots in total, and oops, oh dear. Yeah, I've broken my plots, but yeah, you can see that there's an approximately 50-50 distribution between the 0, 0 and the 1, 1 state, which is what we would expect from measuring our Bell state. We just measure either basis state with roughly equal probability. But we are sampling, so we don't expect 50-50 distribution all the time. We're still flipping a coin on every shot, essentially. Okay, so let's build perhaps a less trivial circuit. So I mentioned the quantum Fourier transform earlier. This, as I mentioned, is an important subroutine in quantum algorithms, so including Shor's algorithm and like fault-tolerant approaches to quantum chemistry, for instance. So we can build this using a polynomial number of these gates. So we need some n Hadamard gates and n minus 1/2 controlled gates for an n qubit QFT. But I'm just going to show the case for 3 qubits. So I can just manually build this. Show the circuit first. So like I said, we have this sort of should resemble a diagram from earlier. So I have a Hadamard gate and then this controlled unitary between qubit 0 and qubit 1, and then there's like this recursive pattern that occurs. So yeah, where was it? Yeah, so yeah, you could, one thing, the less commonly used gates we have to import from this op-type enum, which contains the different types of gate operations. Like this CU1 gate is not accessible directly through the circuit class, so I have to use this add gate method, but that's just a detail. Okay. So yeah, if you want like an interesting sort of programming exercise, perhaps you can try and like write a function that takes in a number of qubits and then spits out the circuit for the n qubit QFT. I think that's like perhaps an interesting problem. So it follows the same pattern. You all have a Hadamard and then a bunch of controlled unitaries, and then a Hadamard and then one less controlled unitary, and it has this kind of recursive structure. So it's an interesting sort of exercise if you're interested in that. So yeah, let's talk about boxes now. So boxes in TKET are for like different subroutines of quantum algorithms. So this Fourier transform is a natural thing that you might want to wrap in a box and then use as a subroutine in a larger algorithm. Yeah, so we support this like box interface, which sort of abstracts away the like raw gates, where it's easier to see what's going on if you're looking at a circuit diagram. So let's build a circuit. Here I've just used a sort of trivial oracle for Grover's algorithm. This is an algorithm for search problems that I mentioned earlier. It's a very simplified version of the kind of circuit that you might see in there. So you have these X gates and then this multi-controlled Z, and then another layer of X's. But we can actually just wrap this up as a subroutine in this circbox class. So we can then pass in our circuit to this circbox constructor, and we end up with the following. So we end up with just a black box called Oracle, which we can then append onto a circuit where we have some other gates in the circuit which you want to apply. So if I click on this Oracle box, I then see the underlying circuit of the box itself. Okay. Yeah, so another type of higher level operation, if you like, is like boxes for just directly synthesizing a unitary. So one thing you can do is just give TKET like a matrix of your favorite unitary operation, and TKET will just synthesize a circuit in terms of gates that implement that unitary there. So I should say this is only supported up to 3 qubits because this is quite a this kind of thing scales like, so if you did it for more qubits, you would sort of have to wait a long time for your circuit to come out. But yeah, let's just synthesize the circuit for this fermionic swap gate here, which is the following definition. So I just pass this into this unitary 2Q box here as like a NumPy array, and then I can just add that to a circuit as a box, and that implements this unitary transformation which I've specified. And if I want to look inside the box, I can just use this decompose boxes transformation, and you see it's now implemented as a sequence of single and 2 qubit gates. Yeah, another thing you might want to do is construct a circuit from CHASM. So CHASM is sort of like a low-level specification for circuits. It's a sort of low-level specification for circuits that's quite widely used. So if we have like a CHASM file, we can just load in a circuit directly from that, and then draw it in TKET here. So here I've loaded in this circuit for quantum phase estimation, which is like another algorithm that's widely used in quantum computing. And so I can load in this circuit here. It's quite a big circuit. But yeah, this is what it looks like. But this is just, I've just loaded in the CHASM file. And then I can sort of count the number of gates in the circuit. So I have 21 gates in total, and 11 of these gates are 2 qubit gates. You can sort of inspect the properties of your circuit like this. Okay, so now that we've loaded in like an interesting circuit, why don't we perform like a more realistic simulation? This is still not very realistic. There's some simplification going on here, but I'm going to run this phase estimation circuit on a noisy simulator. So this is trying to a simulator with some noise model that's trying to capture some of what's going on the device. So I can define a noise model in the following way. So I can use this noise model from IBM Jakarta, and then I can just pass that noise model into Air backend, and then see how the actual device noise affects the performance of my quantum algorithm. So I've used the Air simulator here, as it doesn't require any credentials. So if you're following along, then you should be able to execute all of these cells, hopefully, without having to set up your IBM credentials. Or yeah, hopefully this should be fine. Okay, so for the purposes of this demonstration, I'm going to use a slightly bigger circuit. So here I've just used another phase estimation circuit that uses like 6 qubits instead of 4, as I think this will be help illustrate some of the points I want to mention later on. So if I wanted to see how the different parts of this algorithm are connected to one another, I could use this sort of graph visualization here, which tells me how the different how the different qubits in my algorithm are interacting with one another. So you can see, just like the QFT example I mentioned earlier, we have all possible interactions between pairs of qubits here. So if we're working with a device with restricted connectivity, then we'll need to solve for those constraints before we can actually run our algorithm. So we're actually going to be working with this noise model from IBM Jakarta. As well as the noise model, this implicitly defines the connectivity of the device itself as well. So we have the following sort of layout of qubits that we need to run our circuit on. So now we can just So now we can just use this handy get compiled circuit method on our phase estimation circuit. And we can actually specify a level of optimization as well. So to start off with, I'm just going to use optimization level 0. This just gives you a circuit that will run, but doesn't attempt to reduce the size of the circuit in any way. So you can see if I naively compile this circuit, I have a large number of 2-qubit gates. So I have 136 CX gates in total. So I've now got this sort of larger circuit here. So let's see how this. So yeah, like I said, we now have nearest neighbor only interaction as well. So our circuit will now run on the simulator. So right, yeah. So if we run this circuit now, we see the following probability distribution. So I don't know how many of you are familiar with phase estimation, but we expect to get like a single bit string as a measurement outcome with high probability, and then everything else is ideally sort of a low probability. But you can see because our circuit is very deep, there's a lot of noise, and this is sort of corrupting the results of our computation. So this is the expected answer, but it's not that much more probable as a measurement outcome compared to the other outcomes. So now if we do exactly the same thing, but just specify a higher level of optimization, then TKET will work harder to actually reduce the size of our quantum circuit and hopefully give us a better result at the end. So if I specify this optimization level 2, then TKET performs some optimizations, and now I've got 52 gates in total. So it's about half the number of 2-qubit gates in my circuit. So now if I compare, you can see that it's got much more probable that the outcome is the correct one. So like by reducing the size of my circuit, there's less noise that's accumulated, and I get a stronger signal of my correct answer. So I wouldn't take this simulation too seriously. It's a bit artificial, but hopefully this gives you some intuition of the idea that that shallower circuits can be executed with higher fidelity. Yeah. So like I said earlier, central to TKET's design is its platform agnosticism, if you like. So TKET has this generic backend interface where it's sort of easy to swap between backends. So if I wanted to use this circ simulator instead, then I could do that by just, all I would really need to do is just import that from the relevant extension module, and then all of the rest of the code is the same essentially. I'm just defining this circ backend object, and you see that TKET just converts it to the circ gate set instead of the Qiskit simulator gate set. So yeah, it's fairly easy. You don't have to rewrite a bunch of code to use the different devices simulators. Yeah. So everything all the sort of compilation I've talked about thus far is, if you like, built-in compilation. So you just use the built-in methods that for the different simulators to compile your circuit. You don't necessarily need to think about what's going on. You can just say optimization level 2, and then hopefully you'll get an optimized circuit. But TKET does also allow you to sort of play around with optimizations like individually. So as well as doing, if you like, the built-in compilation, you can sort of compose your own optimizations in sequence to try and improve your circuit. So here's an example. I've loaded in this H2 Jordan-Wigner mapper circuit, which is just a chemistry-inspired circuit, if you like. So, so a reasonably large circuit. It's got 150 gates with 56 2-qubit gates. So you can see it looks something like this. And we can use this very generic optimization pass in TKET called full people optimize. This is a very general purpose optimization. It's supposed to improve on almost every circuit by just performing local rewrites to the circuit. So it, as well as like simplifying like obvious redundancies, like merging single qubit gates, this also does like tries to synthesize like optimal subcircuits as it's traversing the your circuit. So each, so TKET will try and optimize the different blocks in your circuit, as well as performing sort of removal of redundant gates. So I now I've gone from 150 gates with 56 2-qubit gates to, I assume this hasn't executed properly. Oh well. Not sure what happened there. Oops. Jupyter Notebook demo. But yeah, hopefully you'll take my word for it that there are less 2-qubit gates in the optimized circuit. And we can also define oops. Let's see if we can run this again. We can also define like a rebase pass, which is just a sort of a gate set conversion. So each different hardware platform will have its own like set of primitive gate operations. So if I want to define a circuit transformation that converts everything in my circuit to a specific gate set, I can just specify my my gate set like this, and then pass it into this auto rebase pass, and then I'll have a transformation for converting to that gate set. So we have a bunch of like hard-coded conversions, but you can also define your own conversion like manually if you're working with an unsupported gate set. So another thing you can do is sort of compose multiple optimizations one after the other. So I can do this full people optimize to optimize my circuit, and then at the end I could convert my circuit to the gate set that I'm targeting to ensure I have something which can actually run on a device. So you can sort of do this user-defined compilation as well. I was hoping this would be finished by now. Okay, where are we? Oh, looks like we're catching up. Yeah, I have to rerun my notebook. Okay. Yeah, looks like doing okay now. Where was I? Yeah, I think it was here. So yeah, like I said earlier, Qiskit TKET is designed to work well with other libraries. So it's designed to be able to convert between these different circuit formats. So if you're used to working in Qiskit or Circ, hopefully it shouldn't be too hard to try out TKET if you want to as well. So we've just got these handy sort of conversion functions here from the different extension modules. So I can import this TKET to Qiskit and Qiskit to TKET function, and then I can just convert my all of my my QFT circuit from earlier just to a Qiskit circuit. So now you can see I've got a Qiskit circuit here, and I can go in the other direction as well. And this also works for a bunch of different libraries that you might be used to working with. Okay. Yeah, okay. So I've tried to give you some idea of like the sort of base features in TKET, but we also have like some features we've added more recently. First thing I'm going to mention that we've added is arbitrary state preparation. This has been around in other libraries for a while, but we've had some we've decided to implement this ourselves. So this is just a generic state preparation algorithm for generating a circuit to prepare a given state. So if I wanted to prepare this Werner state here, I could just automatically generate a circuit to do that using the state preparation box here by just passing in the state vector, and then this is just automatically generated. I should say that this is, I would recommend a bit of caution here, as this this state preparation algorithm is for generic states is likely to scale exponentially with the number of qubits in your circuit. So this is maybe good for testing, but it will in general generate quite large circuits if you scale up to more and more qubits. Another thing which we have added recently is something we call Toffoli box. So it's a type of box that sort of shuffles around the coefficients in your quantum state. So given a quantum state, we can build a Toffoli box to do whatever permutation of the basis states we want. So here you can say, I can transform a state which looks like this, like the one I mentioned above, to a state that looks like this. And I can just tell TKET to do this mapping here. And then I pass the dictionary into, and I can generate my Toffoli box and then add it to my circuit. And this will take this Werner state to this different state here. So we can shuffle the amplitudes around as we like as well. I think there's actually possibly some publication that's in the pipeline for this, but yeah, it might come out later in the year. Another sort of newer feature we have is support for like ZX diagrams. So I don't know how many of you are familiar with this, but the ZX calculus is a sort of alternate representation for quantum circuits. Certain like simplifications and rewrites become more obvious if you use a sort of ZX representation of your circuit in contrast to the usual gate-based model. So we've got an entire manual section on ZX diagrams, which you can check out at this link. I'm not going to show much code on that, but yeah, that's something we've added reasonably recently. So you can play around with that if you like. Yeah. So that's me just about finished. I'll just in summary, I've tried to give you some overview of the idea of quantum compilation and the challenges of running the different quantum algorithms, and then how to sort of build circuits in TKET using the different primitives that are available, and do some basic simulations, and how to target different devices and simulators. And then at the end, I talked to a bit about actually optimizing circuits and working alongside other libraries in the field. So yeah, just a reminder that you can install TKET and sort of play around with it through its Python package. And here's a bunch of useful links to our documentation and our user manual. So yeah, like I said, everything's on GitHub. So if you want to check it out, then you're welcome to do so. And yeah, I think it's about 10 minutes left. So I'm happy to answer any questions that you might have. Thanks for listening.
Thanks for this great presentation, Callum.
Oh.
I'm checking if there is any question on YouTube.
So I have a question about the Toffoli box, like addition. So could you explain a little bit more about how that works and like what applications again it would be used for?
Okay. So yeah, this is a fairly new feature. So like I said, what this basically does is it can sort of shuffle around the amplitudes of a quantum state. So you can sort of permute all of your coefficients to, you have a box that sort of permutes your coefficients so that you get out some state at the end, which meets the, which, yeah, like if we want to do this permutation, we can construct a Toffoli box as follows. Internally, this is work that's not published yet, but yeah, it uses some like token swapping algorithm where you have like your coefficients on like and then you try and like minimize the number of swaps that you need to do in order to do that. So in principle, you could do everything here using like a classical like just x and CNX, if you like, sort of just the Pauli x operation and the sort of controlled x. You could do all of this permutation this way because all you're doing is permuting bit strings, right? But yeah, there's a more efficient way of doing this in terms of like multiplexer operations, which we have implemented in TKET as well. So in terms of where you might actually use this in practice, I'm not so knowledgeable about this area, but I think it's actually used in sort of, I don't know if you've heard of the linear combination of unitaries approach in quantum algorithms, but yeah, apparently these Toffoli box, these sort of permutations show up in there. Hope that answers your question.
Yeah, thank you so much. Okay. Any other questions?
Is there a question? Oh, okay. So if there's questions on YouTube, will one of you like ask them, I guess, or I can't see any
Yeah,
stream.
I've checked it, but we don't have any question from YouTube also.
Okay.
Okay, well, if people want to learn more, where should they go?
Yeah, so you'll find all of, if you want to if you want to go through any of the material I've covered, you can visit my GitHub repository. Here I've included links to like the API documentation, so you can visit like our website and then read more about TKET and how to use it. We also have a user manual and a bunch of notebook examples as well for different applications you might want to try out. And yeah, I'm happy to answer any questions by email as well. I think I've added my email somewhere. If not, I'll add it to my GitHub repository. But we also have like an open Slack channel as well, and the link to that is in the README of the TKET repository. So you can also join our open Slack channel. In fact, I can probably send a link, and then you guys can share that link as well if you want.
Yeah, that's perfect. A lot of good ways to continue on. Well, I guess we can end there. Remember that we have presentation sessions coming up for everyone else that's on this call. So go out and support your peers that are presenting in the next session. Thank you very much, Callum, for this wonderful workshop. Learned a lot. And we'll see you all at the next session.